Hi, I'm Dave Biesack. I design APIs and developer experience at Apiture. Apiture provides an API-enabled cloud platform that provides web and mobile banking to hundreds of financial institutions and their banking customers across the US. Today, I'm going to talk about JSON Schema's role in APIs and how to wield the double-edged sword of JSON Schema. Perhaps you've heard this quote from Mark Andreessen, the co-author of the Mozilla browser, the founder of Netscape, and internet visionary. Software is eating the world is, at its heart, the essence of the API revolution. All companies are becoming technology companies, and software and APIs are the vehicles for delivering business value, supporting collaboration, integration, interoperability, and competition. As we know, though, over the past several years, JSON has emerged as the preferred transport message format for APIs. It's simple, clean, concise, very flexible, and easily read by computers and humans alike. The JSON Schema org page says that JSON Schema is a vocabulary that allows you to annotate and validate JSON documents. In simpler terms, this means that JSON Schema can describe your data and JSON Schema can validate your JSON data. These are the two edges of the double-edged sword of JSON Schema. To be an API master, one must learn to wield and effectively use both edges of the sword blade. Today, I'll show some specific API design code using JSON Schema and provide some useful tips for wielding the JSON Schema like a master. So first, we're going to talk about JSON Schema's finest edge, and that is validation. Why does JSON validation matter? Well, as you can see, the OWASP API Security Top 10, item number 8, is injection. If you don't validate data coming in from external systems, your API may be subject to injection flaws. It may be an insecure API. So validation is one of many practices of securing an API. It's not sufficient, but it is required. So JSON Schema excels at validation if you wield it correctly. So the first tip I'll give you today is to wield this tool correctly. The value true is a valid JSON schema, but it's not very useful. It means that any valid JSON is accepted. So that degenerate case is not very useful in production APIs. So we need to get a little bit more precise with our validation. So let's talk about honing that validation edge. And the tip here is to use strong constraints. The first constraint in a JSON schema, and the most important, is the type constraint. If you omit specifying the type of a JSON schema, then you have no validation. So instead of using no validation or weak validation, you should apply stronger constraints. If type is omitted, the default is any valid type is allowed. For example, if you specify a set of properties, that does not force the schema to be of type object. Or if you add a minimum or maximum constraint, that does not force the schema to be a type number. It'll still accept non-number values. So you must specify a type if you want to correctly validate your data. In addition to that, there's several other constraints. When you have a number type, for example, you can have minimums and maximums. String types can have min lengths, max lengths, a regular expression pattern, a format such as email or URI. If you've got arrays, you can specify the constraint, the schema of the individual items within the array, the number of minimum number or maximum number of items in that particular array, or that you can specify that the array has unique values. If you're validating objects, you can specify a set of required properties. You can list all the properties and their individual JSON schema constraints. And you can also specify additional properties. Additional properties is a little bit complex, and we're not really going to go into detail of that in this talk. So let's start with an example. Well, I'm actually going to spare you the dread of using pet store examples because, well, just because. Instead, we're going to pick a real world example. And this comes directly from one of Apiture's APIs, which allows a customer to view the set of accounts that they've got at their financial institution. So there's a call to get accounts, and there's a filter on this, which is expressed with a query parameter called product type. And the value can be a pipe delimited list of specific product types. For example, this query will list all of your savings, checking, and CD accounts at the bank. Now, when defining the API for this operation, you can specify the parameters, give it a name, specify that it's in the query, and then you give a schema. And this is a JSON schema to describe that particular query stream. Now, here we've just defined it with a simple type of string, which allows basically any value to be passed along. That's a pretty lame definition of this particular schema. We want to get a little bit more precise and constrain this a little bit better to have both a better and more secure API. So here's an example of refining this parameter definition. Instead of using a string, we're going to define this as an array because we've got a list of values, one or more items. We're specifying here that there's a minimum number of items in the array of 1. The array also must have unique items, and we're specifying a constraint on the items within that array, and they are all instances of our product type schema, which is defined on the right. The product type is defined as a string with an enum, which gives a list of valid values. No other values are allowed. So this gives us a very concise and precise definition of this query parameter, and it can be validated. It also gives developers who are using the API a better information about how to call the API and how to populate this particular query parameter. Also, I'll note that I've taken this product type schema, and rather than simply embedding it inside the query parameter definition, I've extracted it out into a reusable schema in the components section of the OpenAPI. This is useful because this type is also used in query request and response bodies. So it's not embedded directly, but it's referenced. This is an application of the dry or don't repeat yourself principle. So our next tip is then to use middleware such as an API gateway to automatically and unconditionally validate query parameters, request headers, request bodies against your JSON schemas and automatically reject invalid calls. By putting this validation logic into the API gateway, and you can do this with code generation from an OpenAPI definition, et cetera, you don't have to put the burden of that validation in all of your controller code. That means you can't accidentally forget to validate your responses or your request data as they're coming into all your APIs. There's a bonus tip associated with this as well, and that is to validate the response headers and response bodies that you're returning out of your APIs. You can do this as well, and this really helps, especially during development and testing of your API, to ensure that the code is emitting data that conforms to the API definition and the schema constraints that you've identified. So that's the basics of validation. We're going to move on to the other edge of the JSON schema sword, and that is data modeling. I have a couple of assertions here I'd like to mention. The first is that JSON schema is primarily a data validation tool. That is, it validates that the JSON data conforms to a given JSON schema definition. While JSON schema is widely used for data modeling, that's not been its primary purpose or design intent, and we'll see how that affects the use of JSON schema for data modeling next. The first thing to be aware of is there's lots of tools that can help you to take API definitions and JSON schemas and generate some code that models or that defines types and interfaces that correspond to your data models. Open source projects such as OpenAPI Generator or Swagger CodeGen And there's also a JSON Schema to TypeScript tool, provides some of this capability. And there's commercial tools like Swagger Hub and API-Matic. And we're going to talk about some specific examples of looking at some schema definitions and what the code coming out of the Swagger CodeGen tool looks like. So to set the stage, I'm going to talk about a set of APIs around account-to-account transfers. Now, we need APIs for basic portal operations. We want to create, list, patch, or update, and view our transfers via APIs. And that means we're going to need different response schemas to model the responses coming out of the API and different request schemas to model the requests coming from the client. Now, to do this, there's a lot of commonality between these schemas. So we're going to define what's called a transfer fields schema. This is what I call a mix-in schema. It's a schema that's used to mix in or to compose other schemas. It's not actually used in any of the responses or requests directly, but it's used to build other schemas that are used by the API. So a transfer is going to require or typically allow a set of fields. You need a schedule. That is, when does the particular transfer occur, its date, whether it recurs weekly or monthly, et cetera, the amount of the transfer, a memo string that describes the transfer, and a source and destination account. And these fields are going to be reused across other schemas. Next, when we want to create a transfer, we'll use a new transfer schema for the request body. It has a few required fields that it's picking up from our transfer fields mix-in. And we can see that we're using the olive notation of JSON schema to specify that a new transfer schema is composed of all of a set of other schemas. In this case, we've got two schemas, an abstract body that we use for all of our request bodies. So there's a commonality there. And we're using all of the fields from our transfer fields. And this is where we're actually mixing in that mix-in schema that we introduced directly above. There's a few other schemas that we'll need in the API. So our patch operation needs the ability to patch an existing transfer. So it will also have the same mix-in and composition as the others, but it doesn't have any of the required fields that we saw with our new transfer field, which requires you to pass in the schedule, amount, and the source and destination accounts. Our collection schema, which returns a list of transfers, will use a transfer item inside of its array. The transfer item is not an abstract body because it's not the top level response. That's the collection, but it's something that's embedded within it. But it's still going to use or mix in our transfer fields and some other fields as well, like timestamp fields, et cetera. And it's defined as requiring a set of properties. So every item in our collection will include the schedule, the source and destination account, et cetera, as well as the state of the transfer, its created timestamp that it picks up from timestamp fields, and an ID. And those ID and state properties are defined below. Finally, when we want to just get a single instance of a transfer to look at it or maybe to update it, we'll use the transfer schema. And it also uses the same mix-in, but it's inheriting from our transfer item schema to pick up all of the fields that we want for a transfer, including its state, its ID, its creation time, et cetera. And also it's our abstract body schema. So this is what this schema composition looks like. At the top, we've got a couple of these mix-in schemas that we use to compose our schemas. We've got our abstract body, we've got our transfer fields, and below we've got the actual concrete schemas that we use for our request and response bodies for our get, our post, et cetera. And you can see here that all these schemas pick up or mix in multiple schemas. So we're using this olive construct of JSON schema to compose our schemas. But it's important to note that olive is not inheritance. That is, when you're using olive, you can't, in JSON schema, override or replace any of the validation. So if I'm using all of two different schemas, I can't change any of the validation. All of means that all of those schemas must validate the data, and they're validated independent of each other. So we will go down the list and we'll validate our data against each of the items in that schema. And therefore you can't override or change any of that validation the way you think you might be able to do with inheritance by overriding inherited methods. That's just not allowed with JSON schema. So the tip here is to use this olive construct simply for the definition or the composition of your schemas, to define the total or aggregate set of properties and constraints and validation as a sum. But JSON schema has lots of other constructs, and some of them are a little bit tricky when it comes to data modeling. So along with olive construct, there is an any of construct, which provides an array of additional schemas, and any of those schemas must be valid in order for the overall schema to be valid. They don't all have to be, as is true with the olive construct. The one of construct says that of this array of additional schemas, exactly one of them must be valid, and the others must not be valid. Not is used to negate a schema, so you can say it's all of these, but not this other property. And then there's an if then else construct. It's a little bit more complex. We're not going to talk about that today. And then JSON schema also defines or allows you to define custom vocabularies. And you'll note that OpenAPI uses this to define what's called a discriminator. We'll talk about that a little bit later. And then you can also have custom formats in addition to the built-in schemas. OpenAPI specifies a set of formats that it recognizes. And you can also use tuple validation, which is a little bit different. And we're not going to talk about that as well, because it is also very tricky when it comes to code generation to use tuples. So these are kind of the places to take extra care when using JSON schemas, especially if you're concerned about the data modeling and code generation for either your client SDKs or for your backend service. So let's start comparing the effects of code generation using these constructs. We're going to do two comparisons here. We're going to look at a schema that uses olive composition. So here we're going to talk about a single point schema that uses a Cartesian point or a polar point, and we're going to compare using olive to using a schema that uses one of, which is really more the correct way of representing a point in space. Usually a point is represented either as Cartesian format or polar format. And that's what one of says, is one of these must be true, but they don't both have to be true at the same time. So we're going to look at the effects of this code generation. We're going to start with TypeScript. We'll also look at the effects for Java and Go as a couple additional target languages. So when we use the olive construct, again, we're saying that a point consists of the schema of a polar point and also those of a Cartesian point. So the code generation emits an interface for a Cartesian point, which we see here, that has value X and Y values. We're only talking about 2D points at this point. And then we're seeing that the point interface gets generated as an extension of that Cartesian point, and we're adding in rho and theta. So by normal definition of a TypeScript interface, that means a point will have X, Y, rho, and theta. All four of those properties will be in the interface that gets emitted. And that's because we're using all of here, so we want all of those properties. The Java code is going to look a little bit similar. We see we get a class defined here for a Cartesian point with X and Y, and then our point class extends our Cartesian point, and we've got rho and theta. Now, here we've done a very simple composition. There's only two classes, and it's quite easy in Java to have extension of one class extending another. If we get into using multiple classes, then you have to go to interfaces, because classes in Java can only extend one particular class. You can't extend multiple classes. The Go code is even simpler. It defines the point construct, and it does that folding of our olive construct for us automatically. So all of those fields get folded directly in. There actually is no reference here to a point, to our polar point or our Cartesian point. It stands independent of that. So let's go back and look at TypeScript, but now we're going to switch to the one of construct. And this is saying we want a Cartesian point to be either, or we want a point to be either a Cartesian point or a polar point. So our Cartesian point has X and Y, our polar point has rho and theta. And TypeScript is very nice because it can define a type as being an or construct. We can say a point directly maps to Cartesian point or a polar point. And this can extend to 3 or 4 or more types as well. The Java code is a little bit different. Here we're defining a class Cartesian point, but now this says this implements point. And we see below that point is defined as an interface, but it's an empty interface. So point by itself doesn't contain anything. There's no data components to a point, but we've got 2 concrete classes that implement point. One is a Cartesian point with X and Y. The other is a polar point with rho theta. What this means is that you have to, you're extending things, and the second scheme, or the second set of schemas are defined as concrete classes. And so you have to cast a point down into either a polar point or a Cartesian point in order to use them or access the fields. Go is a little bit different. We define a point type as a structure, and it's got both Cartesian and point within it, and then Cartesian and polar points are defined with their fields, but it's not very different from our all of. We still have those same fields embedded within it. So just looking at these differences in what happens with code generation, the tip that I want to recommend here is when you're designing APIs and you're designing JSON schemas, try code generation against multiple languages, not just JavaScript. Don't assume that all of your clients are going to be coding in JavaScript. You have to understand the impact of your API design on multiple client languages, because we have people who are coding against your APIs in lots of different languages. And also consider a mix of dynamic and strongly typed languages. TypeScript and JavaScript are dynamic. Java and Go are a little bit more strongly typed, and they have different ways of generating code to support these constructs. And what we saw with our point class was really that was a form of polymorphism. And we want to be able to use polymorphism in our client code. So how do you really do this effectively? We saw before that if we didn't specify any information about this, we didn't really know if we were looking at a point, whether to treat it as a polar point or a Cartesian point. So in order to resolve differences like that, to support polymorphism, we want to add runtime type identification to our payloads, to our JSON objects. And here we're adding a property to our object, which is named type. And in this case, it's a string, and it has an enumerated value. The type can be either Cartesian or polar and nothing else. And it's also required. So every point object will have a type that tells us exactly what type of point this is. And then there's 2 other additional properties, and these are nested objects. There's a Cartesian object and there's a polar object defined by a Cartesian point and a polar point, which are trivial, and we won't go into those details here. So let's look at the effect of code generation when we add these runtime type identification properties. So on the left, we see what happens with TypeScript. We have a point2D type, which gets defined by the code generation. It's less than an ideal name because it's constructed based on the class that, or the type that it resides in, and then the name of the field, et cetera. So you don't really have a really good name for this particular property, but it does address the purpose. So we have a type field in our point2D type class, and its type is this enum that's defined below. The type enum has a Cartesian and a polar value in it as well. And then we've got our Cartesian object and our polar object that are defined with specific types as well. So that works pretty well for TypeScript. But on the Go side, for example, we really don't get a whole lot of extra benefit here. We have a type property and its type is string, but there's no strong constraints on that particular value. There's nothing that forces it to be either Cartesian or polar as defined in the API definition. So we've lost a little bit of fidelity from our API definition. As I mentioned earlier, OpenAPI has a discriminator. This is defined as in OpenAPI 3.1 as a vocabulary on top of JSON schema. It's a way of extending JSON schema with custom vocabularies or new keywords. And you can use discriminators, and I'm not going to go into details of doing that, but I encourage you to try this out at home. Try some constructs with discriminators and look at the code generation effects for things like TypeScript, Java, Go, Rust, or your other favorite programming language, and see what the effects are of using discriminators. I personally don't use discriminators in most of our APIs, although some may find it very useful. The downside to using discriminators is that not all tools that understand and process JSON schemas also understand the OAS vocabulary. Some do, but some don't. And so you have to be aware of that whenever you look at things that are beyond the standard of OpenAPI, or I'm sorry, beyond the standard of just JSON schema. Make sure all the tools understand those any kind of extensions that are made, such as a discriminator. So the next tip is when you do have things like types or nested objects, embedded objects, etc., is to always give them a name. And this will give you a better developer experience. By giving names, you're avoiding getting names that are at the whim of the code generation tool itself. So here, when we define our type property, I've pulled out the definition of that schema into a point type class, or in this case, a point type schema, defines with the enumeration, and then it's referenced inside the code. The effects on code generation is a little bit cleaner. So now we're using the same names that we used in our schema appear in the generated code. So here's our point type, type with Cartesian and polar on the left, and our property in the middle. In our point 2D class says there's a property called type. Its type is point type, and it's using the names that we've defined. So it's nice and clean and elegant. But again, on the Go side, we have similar constructs. We've got a point type definition for a type, but it's defined just as string. And again, there's nothing here that constrains that particular field inside of our point 2D class to be Cartesian or polar. And that's just an artifact of the code generation tool that we're using. So next, I'd like to point out a little bit of work that's ongoing around data modeling and improving that edge of that JSON schema sword. The first is something called vocab IDL. This is a JSON schema vocabulary to define a data interface definition language, or IDL. Examples would be using JSON schema to create database DDL or data structures in Java, TypeScript, but do so in a more uniform way rather than leaving it outside of the standard or outside the specification. So there's a vocab IDL project on GitHub. I encourage you to take a look at that and participate. It was started about a year ago. There hasn't been a whole lot of activity, but that certainly means that that's an opportunity for us to go ahead and evolve the standard. There's also a vocab IDL channel in the JSON schema Slack, and you can get to that from the jasonschema.org site. There's also a special interest group, SIG CodeGen, that's part of the OpenAPI Discord group online, and you can contact me or your favorite OAS member here at the API Specifications Conference to get an invitation to that Discord group. Finally, there's some related sessions and projects around this stuff. So if you're attending API Specification Conference, look for Ben Henton's talk. He's got 2 different talks this year about JSON schemas. Jason, I'm not sure how to pronounce his name, Desrosier, has a talk on JSON schema vocabularies, how to extend JSON schemas. And as I mentioned, there's several projects out on GitHub related to JSON schemas. The last one here is some of the source for what I've shown in this talk. you can go to that repo and pull down the code and then experiment with it and try it out yourself. So stay safe out there. Please contact me. Feel free if you want to discuss further wielding the double-edged sword of JSON schema. Thank you very much.